Hi, Year 7. This is the fourth and last lesson on sound. I hope you've enjoyed the other few. Today we're looking at echoes and ultrasound. So we need to know what an echo is, how to use an echo to calculate the distance from an object using the formula we did before, distance equals speed times time. We need to look at some examples of echolocation and what ultrasound is and some uses for ultrasound. When you go through the PowerPoint, please could you mark this rag sheet, red, amber, green, on how much you think you know of these topics, and then we can look at them again at the end. So the first thing to think about echoes is that if you make a short sound, a loud sound, especially by clapping his hands, then the sound reflects off this brick wall and back to the person who made the clap. So that's what an echo is really. It's just a reflection of sound off a solid object. So here are the different characteristics of an echo that we need to know. They are reflections of sound waves. This one's reflecting off a building. An echo, if we know how long it takes for an echo to return to the person who made the noise, that can be used to work out how far away the object is. And we use the formula distance equals speed times time to calculate the distance away. So this is how you do it. You make a short sound like a clap. You time how long it takes before you hear the echo. We already know the speed of sound in air is 340 meters per second. So once we've timed it, we know that we want to find out the distance, we know the speed, and we've measured the time, so we can calculate how far away the building is. It's very important that you remember to divide your answer by 2. I'm going to give you a minute to think about it, and then I'll explain why. Why do you have to divide the answer by 2? Well, it's because what we've measured, the time we've measured, is from the sound to the building and back again. So we've measured this whole distance, and we only want to measure the distance from the sound to the building. So we have to divide by 2.
So we're out here, that's the sports hall, on a nice blustery day in the sun to record an echo. So an echo, we're going to hit this snare drum, the sound wave is going to go hit that wall and then come back to the snare drum. And with the time it takes for the sound to get there to there, and you knowing the speed of sound is 340 meters per second, you can tell me how far away that wall is from me here. Are you ready? Go. One more time. So that took 0.3 seconds. So 30 milliseconds. So can you work out for me how far away we are from that wall?
Okay, I hope you enjoyed that demonstration with Mr. Aero and me. I'm going to show you a worked example of how to calculate distance using our formula distance equals speed times time. So this is a useful one. They used to use it in the war, Second World War, for ships to find out where a submarine was and how far away it was. So this is a calculation that they used to find out how far the submarine was away from the ship. So the ship sends a pulse of sonar sound. Okay, it echoes back off a submarine. The ship detects the echo 1.6 seconds later. Now you must remember that the speed of sound in water is much faster than in air. So the speed of sound in water is 1,500 meters per second. Now we do the same calculation. How far away is the submarine? So this is a worked example, so I've given you the formula. We want to find the distance, how far away, so we cover up the distance, and the formula is speed times time. And there it is as well, distance equals speed times time. Okay, so when I do sums like this, I write down the 3 numbers from the formula. So we need to find the distance, a question mark. We've been given the speed, 1,500 meters per second, and we've been given the time, 1.6 seconds. And remember, for the same reasons before, we have to divide by 2, otherwise we get twice the distance away. Okay, so then what I do is I write my formula down, I fill in the numbers that I know, 1500 times 0.8, because I've divided this by 2, and the answer I get is 1,200 meters away. Okay, good. Now, on this slide, I've given you another question to answer. I'm going to put this question on the worksheet as well, but I'd like to leave it here on the PowerPoint. You can look at this question on the PowerPoint and see whether you can do it correctly. It's a very similar one. The climber who is standing here where we are wants to find out how deep the cave is using making an echo and measuring the distance it takes. Now there was a little twist to this question, and that is in cold air, sound travels a bit more slowly. So I've given you a new speed. I've told you how much slower time a sound travels in cold air, because obviously, you know, in a cave the air can be very cold. So sound in cold air travels 5 meters per second slower than it does at room temperature. Okay, I'll leave you to think about that. Remember to go through the PowerPoint, stop at this slide, and try and work it out. Okay, we're going to move on to ultrasound. As you've learned before, the range of human hearing for young people is 20 to 20,000 hertz. So frequencies above that 20,000 hertz are called ultrasound because they're higher frequencies than we can hear, but they can be heard by some animals like dogs or bats. We use ultrasound instead of audible sound because it reflects better off an object and it's more directional than regular sound, so it's just more accurate. Just a reminder of the hearing ranges of the animal kingdom. This bat has got an amazing range of sound from 10 hertz to 100,000, and the grasshopper's got a very narrow range from 100 to 1,000. Here's a human. And for those of you who want to learn a little bit extra about this, you might wonder, because the sound is from 20 hertz to 20,000, why this 20,000 is just a tiny bit above 10,000. It's a bit of a surprise. You might think it would be a bit higher than 10,000. But the reason is this is called a logarithmic scale. And I'll just say quickly, give a little guide about why this bar is so shorter than you might think. Okay, from this line to this line, frequency goes up 10. From this line to this line, it goes up 90. From this line to this line, it goes up 900. And from this line to this line, it goes up 9,000. So you can see that the distances between frequencies here are much closer together than they are down here. So that's called a logarithmic scale. That's just for interest. You'll come across it in maths later. Now we're going to look at echolocation, which is how animals work out how far a fish away, this is a dolphin I think, how far a fish away is by sending out an ultrasound signal. That's where it sends it out. It reflects off the fish and it's received by this little gland, this little organ inside the dolphin. And when you go through the PowerPoint, click on this video and have a look at how it works. Here's another example. This is how a bat sees at night. They also use echolocation, so they emit ultrasound pulses, and they bounce off the prey. This is an unfortunate moth, and then they return to the bat. So the bat can then work out how far away the moth is, and it also helps them navigate away from the side of a cave or a tree. There's some uses for ultrasound that other wavelengths of sound can't do. So one of the uses is to look inside your bodies. It can examine, for example, a fetus inside a mother. So ultrasound waves reflect off the fetus, and then the images of the reflection show you this little baby. So that's kind of a fun thing to see when a mother is pregnant, to see the live baby inside her. Another couple of uses for ultrasound is to treat damaged or swollen tendons, like this guy's done, or you can use it to clean jewelry, and there are other uses as well. Here we go back to our echolocation. with the ship looking for the submarine. But all I need you to remember for this is what sonar stands for. It stands for sound, navigation, and ranging. If you remember back to the bat, just think carefully about it. The sound navigation is just like the bat uses. It uses the navigation part of echolocation to find out if there's a tree or the wall of a cave to avoid. And it also tells you how far away. That's what ranging means. How far away the prey is or how far away the submarine is. So that's why it's called sound navigation, to find out where you're going, and ranging, to find out how far away something is. If you fill a room with absorbent panels, like soft foam works quite well, then they absorb all of the sound. And in this room you can make a recording, for example, with the sound just going into these microphones and not echoing off any part of the room. It's actually a really strange feeling to be inside an anechoic chamber. All you can hear is your heart and your pulse. You can't hear anything back from the room. So this is called an anechoic chamber. Most recording studios have one. So now I'd like you to fill in our little rag sheet again with red, amber and green against the questions that we were going to learn about today. So do you know what an echo is? Fill it in. Could you use this formula, distance equals speed times time, to calculate how far away an object is? Mark your rag sheets. Do you know some examples of echolocation and how they work? Sorry about the one. And lastly, can you give some examples for the uses of ultrasound and what ultrasound is, what frequency it is? So mark the rag sheet. If you feel you didn't do very well, have a look at this picture. If you feel you did pretty well, have a look at this picture. So that's the end of lesson 4, the final lesson on the topic of sound. Just put up a picture of 21 pilots playing in Birmingham 2 years ago, just to remind you how noisy rock bands can be. Thank you very much.